that's what I have up on the board. So first, today we're gonna wrap up section 2.9 from last time, and then you all picked up section 2.10, and you also picked up your practice test. So for next week, you'll have Douglas Williams here on both days, Tuesday and Thursday. And on Tuesday, he'll review the problems with you on the practice test. And I also hope that you all help each other out. You know, you can do the same thing. Someone be responsible for coming up here and writing the numbers 1 through 40, and then you guys can all tick mark which problems are most important to you, and then you can go through those problems in particular. Because some of the problems on the practice test are very easy. You'll just look at it and know how to do it. But some of them will be a little more tricky. And then on Thursday, you'll actually take the test. Well, on Tuesday, the day of the test, what I have done is, so you all grabbed the practice test already? I already made a solutions guide. So I already went through and I did the entire practice test myself. I wrote down all the steps, step by step. And more importantly, I crossed out a few problems. So a couple of the problems I don't think you necessarily have to do. And in fact, I would encourage you just to cross them out. So how will you know what problems to cross out? I will upload this onto Canvas, and that way you can have it for your reference. Now, I still think you should try the practice test problems on your own first, but then you can go onto Canvas and download this, and then you'll be able to look through the solutions yourself. That way you have all the way from now, Thursday, you have a full week to be referencing the solutions guide as well as doing the practice test, and then you'll turn in the practice test on Thursday when you actually take the test. So how does that sound so far? You've got the practice test, you have a whole week to do it. You can work together on Tuesday and with Douglas Williams to review the problems. You have the solutions guide that I'm posting online, and then you'll turn it all in on Thursday. Is that good? I'll post all of this on Canvas, including the solutions guide, so you'll know what problems you don't have to do on the practice test, which ones you should do, and I guess that's it. Any questions about next week? Okay. So what I've done then also for next week is when you guys are here with Douglas, I have already put the solutions up here on the screen. So that might help. That as you go through and you choose which problems you want to see done, you could, as a group, take a look at the solutions, as well as actually doing the problems on the board, but that would help you tease out any questions that you might have. So this is the whole practice test. Oh, I suppose I could show you right now that I crossed out, if you want to write this down, I crossed out number, I crossed out number 27. I can write this down with you. Don't do number 27. And number 28, 34.
28?
Yeah, 27, 28, 34. I've got a list going up there.
Yeah, it's on the back. I know, I was looking for it too.
40 and 40.
They're not in order.
The only reason I crossed out number 40 is because there was a typo. Like the program itself had a typo and the solution there was no solution. Okay, so those 4 problems you don't have to do. I know you're like, geez, thanks, Mr. G. Out of 40 problems, you crossed out 4 of them. But hey, it's not bad. I did the whole practice test in probably, I don't know, hour and a half, 2 hours. I realize it'll take you longer than that, but that's still not overwhelmingly bad in terms of practice and review. All right, so that's your solution guide. You'll all have each other next week and Douglas to go through those problems on Tuesday, and then you'll take the test on Thursday. Well, then that brings us back to today. So everybody picked up section 2.10. Everyone picked up a practice test. I'll post all of this on Canvas after class today. And we can go ahead and get started. So let's see. Did I already tell you the NASA joke? Yeah, I did. Okay, so what do you call a number that can't keep still? A Roman numeral. A Roman numeral. It's a terrible joke. I know. It's probably the worst joke I've ever told you guys. But it is distinctively a math joke, so I felt the need to share it. Okay, so we're going to finish up 2.9. There's only a few problems. I'm really going to focus on which problems we do today. So turn in your 2.9 packet to number 6. Hi, Carmen.
Hi, good morning.
So last night, as I said, I was doing the practice test. I was also looking over the test itself. And based on that, I chose which problems to do with you today in order to really focus our attention on the types of skills and problems that you're going to see on the test. So definitely write all of these down. So number 6, you'll have quite a few problems that are applications of cost and revenue and profit. This one says, given the cost function, which is a parabola, and the demand function, P of X, find the production level that will maximize profit. So again, we have our cost function, and that's C of X equals 1400 plus 450 X plus 0.9 X squared. And then we also have this thing called the demand function. Well, what is the demand function? We might have to remind ourselves. The demand function tells us what? It was very counterintuitive. You'd think it's telling you demand, but what is it really telling you? And the P kind of gives it away. The price you should charge based on the number of units. So this demand function is actually kind of funny. The demand function is telling you the price that you should charge as a function of how many units. Well, what price should you charge? $13.50. And does it depend on the number of units that you sell? No, they're just telling you always charge $13.50. So this is the price you should charge. So that seems to imply that no matter how many units you sell, whether you sell 10 of them or 1,000 of them, you should just always charge $13.50. All right, well, they would like us to maximize profit. That's the question, right? It says find the production level that will maximize profit. So what we want to do is maximize profit. So obviously we need an equation for profit, and then we would have to take the derivative, find the critical point, and then find the maximum. So what's the equation for profit? What is in general the equation for profit in English? How do you find profit?
The sales price minus, or like minus the cost of the product.
Yeah, that's it. It's the revenue minus the cost. Yeah, your revenue minus your cost. That's always profit. Profit is how much money you take in versus how much money you send out. So that's your profit. We'll call that P of X. And so in this case, well, what is our revenue? Revenue is how much you charge per unit times the number of units that you actually sell. So what we could do right here, just to further conceptualize it, is that it's the price times the number of units that you sell. That's what revenue is, minus the cost. So what was the price? $13.50. That was our demand function. And the number of units is just X. So we have 1350X minus the cost, which they told us is that whole thing. Why is it important that you put this whole cost in parentheses? Yeah, you have to remember to distribute the subtraction to every single term. If you don't use parentheses, you might accidentally only subtract the 1400 and leave the 450 and the 0.9 positive, which would be incorrect. So really important that you distribute your minus. So we now have a definite function for profit. Profit is, let's see, 1350x minus 1400 minus 450x minus 0.9x squared. So I'm going to go ahead and write it in order. Minus 0.9x squared. And then 1350 minus 450 is what? Plus 900x. And then minus 1400. Did I do that right? Is 1350 minus 450 900? I think so. All right, so there's our profit. Now, folks, I want you to appreciate how much work did we have to do just to get to the point where we can finally take the derivative. A fair amount of work, right? We had to remember what the demand function was, recognize what our goal was, come up with our own profit equation, and that is you have to remember that revenue is the price times the number of units, and then put it all together. So there's quite a bit that you'll have to do on your own just to get to the point where you can then take the derivative. So now we can take the derivative, which would be what? Negative 1.8x plus 900. And since we want to maximize profit, you take the derivative and set it equal to 0. Now, in my practice review, folks, or on the solutions guide, you'll see over and over I took the derivative, and then I set it equal to 0, and I put it in a box. I did that as my own way of highlighting what I was doing. It's like I was trying to say to you, okay, I took the derivative, now I set it equal to 0, and I'm going to solve it. So I just want to draw that to your attention. So now I'll go ahead, move the 900 over to the other side. So I have negative 1.8x equals negative 900. Divide off the negative 1.8.
Negative 500.
Positive 500?
Negative 500.
Positive 500?
Positive.
Good. I hope it's positive 500 because it's the number of products that we're selling.
Negative.
Yeah. Okay, so we should sell 500 units to maximize profit. Technically, we've already answered the question. It said find the production level that will maximize profit. What's our production level? 500. But let's go one step further and actually state what would that profit be. So what would the profit be at 500? So right then, you could go ahead and write P of 500. Again, I'm telling you how I wrote it on the solutions guide, so you recognize it. That's just a very quick way of saying I want the profit at 500 units. And then you don't have to show a ton of work for that. You can just take out a calculator and type it in directly. So we have our profit formula, negative 0.9x squared plus 900x minus 1400. And on the solutions guide, I didn't necessarily show a ton of work to accomplish that. I just went ahead and typed it into my calculator and got a number. So let's see what that would be. If I plug in 500 into the profit, that'd be negative 0.9, 500 squared plus 900 times 500 minus 1400. Maybe you'll tell me if you got the same thing. I got a profit of 600. So there's kind of two answers. I realize the question only asked find the production level, but it'd be pretty natural that you would go one step further and actually state what that profit would actually be. This is a good, solid problem. This is a real good business calculus problem. This is the real bread and butter of what we do in business calculus. Questions or thoughts or feelings?
You plug it into the px the negative 9.
Yeah, I plugged it into the original profit formula. This is the profit formula. This is the derivative of profit, but this is the profit formula. Now, P.S., what do we call the derivative of profit formula? This is actually called something. When you take the derivative of profit or cost or revenue, we call it, what is it? Marginal. Yeah, this is actually marginal profit. So just make a note for yourself that marginal profit, the book and the program sometimes call that MP. They sometimes call that MP. That's marginal profit. The word marginal actually means derivative of. So marginal profit is the derivative of profit. Marginal cost is the derivative of cost. Marginal revenue is the derivative of revenue. Nick?
Did you plug in the P of 500 to not the derivative of it, right?
No, not into the derivative of it. I typed it into the... If I did plug it into the derivative, what would I get? You can take a guess. If you plug 500 into the derivative, what would it equal? After all, we just said that 500 was the maximum point. That's where the maximum is. And the derivative tells you the slope. So what is the slope at the maximum? What is the slope at the maximum point, Nate? What's the slope at the maximum? Anytime you look at a graph and you look at the maximum, what's the slope right there? 0. So what would happen if I plugged 500 into the slope formula? You get 0. So yeah, I definitely didn't plug 500 into the derivative formula because it would just equal 0. So instead, you plug it into the actual profit formula because that's what you're looking for. Okay, good question, folks. Well, let's keep going. That was number 6. We're going to skip number 7 and do number 8. Without coming right out and telling you that number 8 is a question on the test, there's a chance that number 8 is the type of a question that you can see on the test.
Is that why they have blue stars on it?
I put the blue stars to show which ones I definitely wanted to do today. It doesn't necessarily mean it's a test question, but it's the type of thing I wanted to do with you before the test. All right, so I'm going to erase all that now. You didn't get it down, you can watch the video with this wonderful high-quality webcam, which now gives really good quality. Have any of you watched the video since I changed to a webcam?
Yes.
The video quality is much better. You can actually see what's on the board. All right, so this is a great question because it gets at what businesses try to do. So here, it's a manufacturer has been selling 2,000 television sets a week at $510 each. So that's what's been going on. You've got this manufacturer, who knows who it is? It could be Sony or any other manufacturer. And they've been selling 2,000 TV sets a week at $510 each. But then all of a sudden, a market survey indicated that for every $12 rebate offered, the number of sets sold would increase by 120. So that's a positive, right? If all you have to do is offer a rebate, a small rebate too, that's only $12, that more people would buy the TV. Because what happens when you offer a rebate? What?
Less money.
It's less money for you, that's true. But what happens when you do offer a rebate, like in a newspaper or an advertisement? You sell more, right? People get excited. They're like, oh my gosh, there's a rebate? I'm gonna go buy a TV. I wasn't gonna buy a TV, but since they're offering a rebate, I'm gonna go get me a TV, right? So a rebate is a way to get more customers. So everyone, let's start by capturing this information in the form of a graph. So we know that, there we go. The very first data point we have is that they sold 2,000 TVs and at the cost of $510. This is important that you draw the graph. I don't know how else to do this problem unless you're drawing a graph and visualizing what's happening. So let's draw this graph together. That's our first data point. This manufacturer, if they sell 2,000 television sets, that's the number of sets, then they sell it at $510. Okay, well, what's the next thing they said? The market survey indicated that for a $12 rebate, the number of TV sets would increase by 120. So now, how many TV sets are we selling? 2120. Yeah, 2120. Now we're selling 2120. And how much are we charging? Since there was a $12 rebate. Only $498. Right? So now we have two data points. And the assumption here within this problem, it says find the demand function, P of X, where X is the number of television sets sold. So the demand function is how much should you charge? And they say assume a linear model. So what can I draw through my 2 points now? A straight line. They're saying assume a linear model that as I offer a rebate and charge more and less, the number of TVs I sell will increase and decrease according to a linear model. So what we need now is to go ahead and find the equation of that line, because that line is the demand function. When they say find the demand function, that P of X is actually mx plus b. It's a linear demand function. It's telling you how much you should charge in order to sell that many TV sets. So let's start by writing out y equals mx plus b. You will have to come up with your own demand function for this. So what should we find first, m or b? What is it?
M.
Yeah, we always have to find m first. And m we can find pretty simply visually just by looking at our graph. The slope is down 12, right 120. Right? Because we offered a $12 rebate and we sold $120 more. So that means my m value is down 12, right 120, which is negative 0.1 or negative 1/10. So there's my slope. Y equals negative 0.1 x plus b. And now how do we solve for b? Yeah, you have to plug in an x and y. Well, one of my coordinates was 2,000, 510. And my other coordinate was 2120, 498. So now we can choose either one of those coordinates. Which coordinate do you like better? I like the 2,000 as well. It's just a nice round number. So now we have 510 equals negative 0.1 times 2,000 plus b. And this is going to allow us to solve for b. So now we have 510 equals negative 200 plus b. And so you add the 200 over to the other side. And this tells us that b is equal to 710. And therefore, our whole equation is y equals negative 0.1 x plus 710. And what is that equation? It's the linear model for the demand function. So this is actually P of x equals negative 0.1 x plus 710. This is the price you should charge. Furthermore, what does the 710 represent? I mean, on the one hand, 710 is the y-intercept. And what does it mean realistically about this problem? How many TV sets can you charge, or can you sell if you charge $710? A big fat nothing. So 710 is too much. No one in the world is willing to pay $710 for that TV set. You have to lower the price significantly before you're able to start selling TV sets. Okay, well, this is wonderful. The first question, A, said, find the demand function P of x, where x is the number of TV sets sold, and assume a linear model. So that's the answer to the first problem. Now, I asked you all to draw a graph because I said, in my opinion, this is the only way to do the problem. But I can imagine you're saying to yourself, no, Mr. G, I didn't have to draw that whole graph. I knew the slope was down 12, right 120, because they told me right up front that if you offer a $12 rebate, you sell $120 more computers. I don't need to draw that whole graph. I can get the slope from just reading it because I already know it's negative 0.1. But then, remember, you're going to have to plug in a coordinate for x and y. So how are you going to keep straight that it's 2000, 510, not 510, 2000? How are you going to keep those two things straight? I think that's why a graph offers so much benefit. That by drawing a graph, you clearly show your brain, your audience, what you're talking about. So I really do recommend that you draw a graph when you do this problem. Okay, let's move on to the next question. This is the exciting one. B, how large of a rebate should you offer in order to maximize revenue? How large of a rebate should you offer in order to maximize revenue? Well, let's take that in two steps. First of all, what's the formula for revenue? Revenue is, in words, what times what? Revenue is just the money that's coming in, right? So revenue is the price you charge times, not the cost. We're just strictly bringing in money, the number of units you sell, right? Because if you're charging $500 per TV, all you need to know is the number of TVs you sold, and that's your total revenue. So the total revenue, this is well worth writing down and memorizing. Your total revenue is the price per item times how many items you actually sell. So in this case, our revenue, R of X, what is our revenue? Well, what's the price we charge? The price we charge is this, our linear model for the demand function. That's how much we're charging. We're charging, as a function of X, we're charging negative 0.1 X plus 710. That's the model for how much we're charging. And how many units do we sell? X. So that's our revenue. We go ahead and distribute the X. So it's negative 0.1 X squared plus 710X. And that is telling you how much money you're actually bringing in. By multiplying the price you're charging per TV times the number of TVs that you sell, that's your total revenue, and so we get this quadratic model. Of course, we were asking how to maximize revenue. So obviously, what did the shape of the revenue graph have to be if we were going to maximize it? It would have to be some sort of parabola, right? And sure enough, we did end up with a downward-facing parabola. So this works. We can now find the maximum. And how do we find the maximum? Find the first derivative. And so you would go negative 0.2 X plus 710, and you find the first derivative, and you set it equal to 0. And again, on my study guide for you guys, I boxed it. Every time I was about to do something, I would box it. I'd say, okay, I found the first derivative. It's that, but I'm setting it equal to 0, and now I'm solving for X to find the critical value for X that will maximize our function. So now we have negative 0.2X equals negative 710, and divide off the negative 0.2, and we get
3550.
Yeah, 3550. Great. So that's what? The cost per TV? Is that $3,550 per TV?
No, that's the number.
No, that's the number of TVs. That's how many TVs we should sell. Which is impressive. Look at that. That's a lot more than we were selling. That is way more TVs than we were selling. But apparently if we want to maximize our revenue, obviously you'd want to sell a lot of TVs. But that's not the end of the story. If that's the amount of TVs that will maximize our revenue, what would we want to know next? Yeah, the price and how much of a rebate is that? Because that's really what we're still asking is how large of a rebate should you offer in order to maximize revenue? So now that we know that $35.50 is how we maximize revenue, now we go back and we look at the price. What is the price? That'll be P of $35.50. And so therefore the price that we should charge is negative 0.1 times $35.50 plus 710, which is negative 355 plus 710, which is what? $355. That's how much we should be charging for a television set, is $355. So remember, the question we're asking is how large of a rebate should you offer in order to maximize revenue? Well, we now know how to maximize revenue. It's selling 3,550 computers, TV sets. And therefore the price, if you sell 3,550 computers, TV sets, is $355. So going back to our graph, if we're gonna sell it at $355, first of all, continuing our linear model, we know that that's way over here at a total of 3,550 computers, TV sets. And therefore, how big of a rebate is that? From 510 down to 355. Yeah, the rebate, therefore, is 510 minus 355, which is
155.
Oh, 155. Yeah, 155. That was a solid math problem. That was an incredibly solid math problem. We're not even done. There's part C. But just to really appreciate, we did some amazing computation right there. All we had was some market research was that if you gave a, what, $12 rebate, your sales would go up. And based on that market research, we came up with a linear model. We assumed it would follow the same model. And based on that model, we decided how to maximize revenue. And based on how much that revenue was, we used our model to figure out how much we should charge. And based on that amount that we should charge, we said, this is how large of a rebate we should offer. That's quite a problem. Like, that's a really good math problem. Okay. Well, the last part, I'm going to go over here and erase some of this. The last part is what? If the weekly cost function is that, how should it set the size of the rebate to maximize its profit? Boy, that doesn't sound very good English. If the weekly cost function is that, how should it set the size of the rebate to maximize its profit? Okay, so now we're not just asking how do you maximize revenue anymore. Remember, the $155 rebate was in order to maximize revenue. So now this is a completely separate problem. Now we're asking how do you maximize profit? Well, what is profit again? The definition of profit is revenue minus cost. And we do now know, so profit is revenue. We have a formula for revenue. It's negative 0.1 x squared plus 710 minus the cost. And this cost function is parenthesis 170,000 plus 170x. So that's our profit function. Revenue minus cost. So we distribute the minus sign. That's kind of nice. It cancels out oh, it doesn't cancel out anything. That's 170 and that's 710. So our profit is negative 0.1 x squared, 710 minus 170. Is that 540 plus 540x minus 170,000. Did I do that calculation correctly?
Yes.
Okay. Okay, so that's our profit formula. So how do you maximize profit? You do what? Oh, how do you maximize any function? You take the derivative and set it equal to 0. So now my derivative is negative 0.2x plus 540, and I set that equal to 0. So I have negative 0.2x equals negative 540, divide off the negative 0.2, and I get x equals what? 2,700? By 40 divided by 0.2? Yeah, 2,700. So what do you notice about the difference between maximizing profit versus maximizing revenue? So this was to maximize revenue. This was to maximize profit. Are they the same? No, interestingly enough, they're not the same. Should you normally expect the maximum revenue and the maximum profit to be the same amount of units? No. Probably not, because they're two totally different things. Because if I sell 3,000 TV sets, my cost is going to be more, which is going to take away some of the profits. Whereas by doing fewer TV sets, I'm actually maximizing profit. So that's really interesting. What would you rather do in your own business, in your own life? Would you rather maximize revenue or profit? Probably profit. The first thing you'd probably think is, why not profit? Because if I sell 3,550 computers, TV sets, I'm not making as much profit, but I want profit. But on the other hand, what if you care about market share? What if you're like, forget profit? I want everybody to know my name. I want everybody to know that my TVs are the best. I want to sell so many TVs that everybody just thinks, oh, JW's TVs. I mean, obviously, you get a JW's TV. So is it, it depends on your long-term goals, right? If you just want money, you'd maximize your profit, but your market share wouldn't be as big. If you want to capitalize on your market share, you'd go to boost your revenue, because then more people know your name, more people have your product, and then word of mouth is going to help you sell more in the long run. Nate?
Is that the answer for number C? Because
Part C said, how should you set the size of the, oh, thank you. How should you set the size of the rebate? No, we're not done yet. So that's how many products. And so we would have to find the price. So let's find the price at 2,700. So the price at 2,700 is, now this is the price function, not the profit function. Lowercase p, this is the price function. So it's negative 0.1 times 2,700 plus 710. So the price should be 440. And going back to my graph, now see, isn't it helpful to have a graph? We're able to put all this stuff in perspective if we have a graph and we're keeping track of all of our data. At 400, that meant we were selling 2,700 computers. And so how big of a rebate was that to go from 510 down to 440? $70. So the rebate was $70. For all I know, all of you already agree with me that the graph is a good idea. But dang, this graph looks good. Doesn't it? Yeah, I know. It has all the information from the whole problem that we've been doing. Folks, that's a really good math problem. This is why people would get paid to do this. This is why people hire accountants and business managers, because these are all the decisions that you're making. What's that, Julie? Oh, nothing? Okay. All right, well, that's number 8, folks. Video caught it all. If you'd like to go back and take a look at it later, you certainly can. Let's keep going. We're going to skip number 9 and number 10, and we're going to look at number 11.
Oh, quick question.
Carmen.
For 2,700.
Yes, for 2,700.
Where did you put that back?
Where did I what?
Which formula did you put?
The demand formula. No, wait. Where is it? My demand formula. I don't have it written down anymore. Yeah, I erased it. It's the demand formula, because you wanted to know the price. The price. So it was the price formula. Here, Carmen, it was the demand function, which I believe was negative 0.1x plus 710.
Yes.
It was our linear model. the linear model, that's the price. Capital P is the profit, and lowercase p is the price. Isn't that just terrible, folks? What's the difference between a capital P and a lowercase p? Not much. So that's something you need to be careful about. All right, number 11. The function p of x, now what is that asking for? Since it's capital P, we're talking about profit. We're talking about profit. So it says the profit is given by that, and that makes sense because what's the overall shape of that graph? The shape of this graph is a upside down parabola. So therefore, we should be able to maximize our profit because you find the top of the parabola. And it says gives the profit when X units of a certain product are sold. Might as well make it computers. So find all those things. I'm not going to actually necessarily calculate all of these with you, but I just want to look at it. So if you want, okay, I'm going to write it down. Profit is negative 2.25 x squared plus 1,000 x minus 8,000. Part A, it wants the profit when 60 units are sold. So how do you find that? You just plug 60 in. So it'd be P of 60. Now, on the test, and in general, you're sitting at home doing Math AS, you're in here taking a test. Do you need to show all of that work? Well, probably not. I mean, what are you all going to do? You're all just going to plug it into your calculator, aren't you? So it'd be negative 2.25 times 60 squared plus 1,000 times 60 minus 8,000. And if you just write down the answer of 43,900, that's okay. You know, you don't have to sit there and show me plugging in 60 and showing step by step arithmetic work. You can just go ahead and tell me by using your calculator. Is that fair? That's work you don't have to show. All right, so that was the profit when you sell 60 units. What's the average profit? How do you calculate the average profit? That'd be P of X divided by X. Would that be the formula? You take your profit and divide by the number of units you sell. That's the average. And therefore, in this particular case, you can just use your number from the previous problem. And this is a very simple, straightforward calculation to do. You don't have to calculate P of X again. You already had the answer. So you're just taking that previous answer and dividing it by 60. It's still on your calculator. You just hit divide by 60. And now you know that the average profit is 731.66 repeating. Here's another note. Anytime you have a repeating decimal, I want you folks to use that line, the bar on top, because that reminds you that it's 0.66666 repeating. If you were to now use this number in another calculation, then in the next calculation, you won't just type in 731.66. You'll type in 731.6666666 and use that in your next calculation so that you're not losing information and you're not rounding. So definitely use your repeat bar to remind you that that number goes on.
Will they take points off if we're not?
Well, no, but your answer will end up not being as accurate. Like, for instance, what if someone just wrote down 731.67? Your answer is already wrong. I mean, it's not wrong, but it's off by a little bit. It's off by a little bit. And if your client is paying you for information, I don't think they want you to make any rounding errors. Yeah. All right, so that was our average profit. What about the rate that profit is changing when 60 units are sold? What does that mean? The rate that profit is changing. Is what, Nick?
Slope.
Yes, the slope. And therefore, we will calculate. We want the slope of profit. So if this is my profit graph and I want the slope at a particular point, that means we're calculating the derivative. So part C, the rate that profit is changing, that's just the derivative of profit. And the derivative of profit is negative 4.5x plus 1,000. That's the derivative of profit. That's the rate that profit is changing. And they want it when 60 units are sold. So we're plugging in 60, negative 4.5 times 60. Now, again, when you're doing calculations like this, I naturally assume you're going to use your calculator. So the important thing would be to show me how you calculated the derivative. You know, show me a derivative formula. But then if you were just to write down P prime of 60 equals 730, that would be okay too. So long as you show me the actual derivative formula first. So that was the rate that profit was changing. And the fact that this number is positive, what does that tell you? 60 units. Yeah, it's still increasing. So 60 units is over here on the increasing part of the parabola. We have not yet reached our maximum profit yet. So 60 units is definitely not the maximum profit because the rate that profit is changing is still positive. So in the long run, we would want to sell more units than 60. All right, how about D? The rate that profit changes on average. Ooh, this is a good question. The rate that profit changes on average when the number of units sold rises from 60 to 120. Folks, to do this problem, I recommend all of you draw a graph. If you haven't already done so, draw a quick graph, show a parabola, show the 60, which is still on the upswing. And now we're saying, how much does slope change when we go out to 120? So when we go out to 120, we have a different point. And what does that mean to find the average, the rate that profit changes on average? So what do we calculate? This is more old school. Secant. Yeah, now we're calculating the secant slope. This is a low-tech problem. They're not asking for a derivative. They're asking you to literally calculate the slope from the point at 60 to the point at 120. So you would want to find, well, let's see here. The point at 60 was 60, 43,900. That was that coordinate. We'll actually now have to go ahead and calculate the coordinate. So we have to go back and calculate our profit when it's 120 units sold. So negative 2.25, 120 squared plus 1,000 is 120. That's 8,000. My coordinate that I just calculated, which is wrong. Negative 2.25. The coordinate I just calculated is 79,600. So we now have two coordinates on our graph. Again, this is why I think drawing a graph is so helpful. We have two coordinates, and now we can very easily do the slope formula. So the slope formula, y2 minus y1 over x2 minus x1. Isn't it nice to see the slope formula again? It's like been so long since we've looked at the slope formula. It's kind of bittersweet. So clearly my profit went up, right? We know it's a positive slope because we went from 60 to 120 and the profit went up. So that would be 79,600 minus 43,900 all over 120 minus 60, which is $595. That was the rate that profit changed on average when you went from 60 to 120. Now, folks, to be fair, do I know that my drawing is correct? Is 120 actually on the other side of the maximum? Do I know that? All I know for sure is that it did go up. The slope was positive. But couldn't it be that 120 is actually here, still before the maximum? Yeah, it could be. I had no idea when I was drawing that picture that it was correct. In fact, I even made an assumption that it was going up. Well, no, I guess I knew it was going up once I calculated the value. But knowing that secant, we actually don't know yet if the maximum is in between it or if the maximum is still on the other side of it. And so that's finally part E, the number of units sold when profit stops increasing and starts decreasing. Well, what is that? That's a really nice way of saying it. What does that mean, that profit stops increasing and starts decreasing? Yeah, that's the maximum. Think.
I just have a quick, what did you plug 60 and 120 into to get 79,643? Which formula again? Like the first step.
Where are you? Right there?
Yeah.
Oh, well, this is the actual profit.
Yeah, so into 2 point.
Yeah, into the actual profit formula. Yeah. Okay, so now finally part E, they're asking for the maximum profit. So we already have our formula for the derivative of profit. It was negative 4.5x plus 1,000. And so we just set that equal to 0. which again, I'm kind of boxing off. I'm saying I'm taking my derivative, and then I'm setting it equal to 0, and I'm solving for x. So that's negative 4.5x equals negative 1,000, and divide off the negative 4.5, and you get x equals something. I got 222.222222222. So given that, which of my drawings is correct? Yeah, this one, because the maximum is still on the other side of 120. The maximum is still quite a ways away. It's at 222 units. Now, can I sell 222.2 units? No. So here's an important point. Since my formula told me that in order to maximize profit, I would want to sell 222.2 units, but I can't sell part of a unit. So I have to round. But the question is, do I round to 222 or do I round to 223?
I would want 222.
You might think to round to 222. You might think that because you round to the nearest whole number. But the fact is, I've already done some of these problems, and I'm always checking. I always check. Since they say maximum profit is 222.22, I plug in 222 and 223, and it's varied from situation to situation. Sometimes the maximum profit was actually if I bump up, and sometimes the maximum profit was actually if I bump down. And one time in particular, I remember when making the answer key, I had to round the wrong way. Even though 0.2 would round down, I actually had to round this way to actually maximize profit. So since you cannot actually sell 0.2 of a product, you need to actually check both. You need to check both right now. Plug 222 in and plug 223 in and see which one has more profit. So I'm going to go ahead and do that. If I find P of 222 versus P of 223, right now I realize some of you might not even believe me. You say, no, come on, Mr. G, stop. It's obviously going to be 222. You round down. But, and I can't guarantee that this one is going to work out this way, but I am telling you for sure that I've already come across multiple problems where I had to round in the counterintuitive direction to actually maximize profit, and so that's why I'm telling you it's important to actually check. So I'm going to go ahead and plug in 222 and 223 and see what I get. 222. Oops. When I plug in 222, my profit is 103. Whoops. 103,111. Whereas when I plug in 223, my profit is 103,109. Okay, so in this particular case, it was correct to round in the direction that you expected. So the true answer, the number of units sold when profit stops increasing and starts decreasing, well, the answer to that question is 2.2.22222, because that's when profit stops increasing and starts decreasing. But if you were to actually advise someone on how many units to sell, what would you advise them? You would advise them to sell 222 units. Yeah. Okay.
For the test, can we just leave like 222.22?
I think you should go a step further and say, this is the technical answer for when the slope is 0. But if you were to advise a client, this would be the maximum profit.
So we have to do it on the test?
I think you should. I think it's thorough. Yes, I do it on the test. Yeah, do it on the test. Because you folks, you're the business leaders of America, right? You're the future business leaders of America. I want you to do your mathematics now as if you're already in that position. I want you to be very thorough when you do your math.
I'm referring that 222 in the original problem, right?
Yeah, the original problem, because you're wondering what will actually maximize profits. Yeah. Carmen, I understand your question. Nate, I understand your question. I'm sorry. You guys, I'm not trying to be like a drill taskmaster or whatever, but I am thinking about like what's good mathematics? What's really good mathematics? What would make you guys really impressive mathematical business leaders? And that's going the extra step. That's going the extra step to actually think about profit.
I just lazy, don't want to do it.
Carmen, I so appreciate your honesty. I really do. You are more honest than you are lazy, Carmen. How about that? All right, folks, let's keep going. 2 more problems from this chapter, and then we're going to do 2.10. Okay. Thank you, Nate, for your question. Carmen, your question. Does anyone else have a question on this part?
Am I doing this wrong? I need a different number for 3222.
Oh, no, I want for 3222 or for 2222? Negative 2.5 squared plus 1,000 minus. Oh, you got very different numbers. But you, let me see my computer. My calculator. Oh, it's 2.25.
Oh.
Wow, that's crazy that it made that big of a difference. You got a wildly different answer than I did. And yet that's not a huge difference. Oh, what do you know? That actually did make the difference. 2.25 versus 5 made a huge difference in your answer. Isn't that crazy? All right. Folks, I'm also, all these things that I'm telling you the way I wrote the solution key as well. So you're going to see that I did that work to compare two different profits. And so I'm telling you all this stuff so you know how to look at and read the solution manual that I gave you for the practice test. Okay, so here we are, the Sunglasses Hut. Folks, isn't that a real company, the Sunglass Hut? Did any of you ever buy sunglasses there?
Yes.
A long time ago? Nick's like, no, they haven't. I haven't either. But I remember seeing it at the mall. So they have a profit function given by, so that's our profit, where Q is the number of products you sell, and it's negative 0.02 Q squared plus 6Q minus 49. Q is the number of thousands of pair of sunglasses sold. And P is the profit in thousands of dollars. So that's just something to keep in mind, that both of these units are in thousands. So that's actually thousands of sunglasses. And this is actually thousands of dollars. So just keep in mind that the numbers are going to be small. It's going to say sell 20 sunglasses. That doesn't really mean sell 20 sunglasses. It means to sell 20,000 sunglasses. Okay. Part A, find a simplified expression for the marginal profit. Oh, good. Just like I mentioned earlier, they might use MP, and marginal profit stands for marginal, which is really the derivative of profit. Yeah, marginal is the derivative of profit. Folks, oh, speak of the devil, I was about to say, where is Rose? Rose is not here again. I'm sorry, Rose, to hear that. All right. So we're going to find the marginal profit, and even though they wrote MP of Q, I'm going to go ahead and write P prime of Q, because I want to remind us all that marginal profit just means the derivative. So what is our derivative? Negative 0.04 Q plus 6, and that's all they wanted. Find a simplified expression for the marginal profit. So as far as part A goes, I don't have to set it equal to 0 and solve it yet. That's just it. Is that right? Yeah, I think that's correct. Okay, part B. How many pairs of sunglasses should be sold to maximize profits? Okay, so now we do set this equal to 0. We would set negative 0.04 Q plus 6 equal to 0, which gives us negative 0.04 Q equals negative 6, dividing off the negative 0.04. Which gives us that Q is equal to 6 divided by 0.04, 150. What does that 150 really mean? 150,000 sunglasses. Okay, so how many pairs of sunglasses should be sold in order to maximize profits? 150. And then part C, boy, this is a very nice and simple problem. This doesn't have nearly as many steps as before. Nate?
Do we write it as 150 or should we write it as 150,000 pairs?
You know, that's tough. That's a real good question, Nate, because Q is absolutely equal to 150. 150 is Q. But if you were to write the answer in English to tell someone, you'd say, oh, the answer is 150,000 sunglasses. What you wouldn't want to do is write that Q is equal to 150,000, because Q is equal to 150. But if you're just writing out the answer in English, then that would be the answer.
So either or.
Either or. So what is the actual maximum profit? What do? To find the profit? plug it right back into the original, right? So we're going to plug in 150. This is the important thing. See, if you plugged in 150,000 right now, that would give you the wrong answer. So we're going to go ahead and plug that in. Folks, I'm going to share with you a shortcut that I've been using myself personally on my calculator. And maybe you're like, yeah, Mr. G, I already knew that. You don't have to tell me that. But see, what I do is that whenever I'm going to use the same function over and over again, I don't type it into my computer over and over again. I go to y equals. Oh, good timing. I go up to y equals. I type in the actual formula, negative 0.02 x squared plus 6q minus 49. And I graph it. I just go ahead and graph it because then I have a visual of what it looks like. And then once I have a graph, I do my second calc option. You know, above the trace button, it says calc. I do second calc, and it says value. I hit value, and then I can plug in whatever I want. I type in 150, and it immediately just tells me the answer, 401. So that way I don't have to keep typing it into my main screen over and over again. I almost always go to my graphing calculator, graph it so I see what it looks like, and then I use second trace in order to just type in values. So I find that for me, that's a very huge time-saving device. I recommend you practice that and try to learn how to do it. Okay, well, that's it. So what does that mean? 401,000. So there. Thank you, Nate, for asking. See, the answer is P of 150 equals 401. But in terms of actual English, you'd say $401,000. There's only one more problem on this section. Let's just go ahead and finish it, and then we'll take our break. That way, psychologically, we're done with that section, and then we'll move on with 210. So this last problem, number 14, well, actually, we might not even have to do it. It says, suppose a company's revenue function is given by that. So that's your revenue, and the cost function is given by that. Find an expression for marginal profit. Let's do it. It's so simple, and I really hope that this is burning its way into your brain. But these methods, you're memorizing them. You're like, yeah, I got it. Profit is revenue minus cost, and so on. So I'll do the problem over here so I don't have to erase it. Number 14. It says, find a simplified expression for marginal profit. Well, first, what do we have to do? First, we have to just find profit. So profit formula is going to be revenue minus cost. That's a nice way of writing it down right there. Profit is equal to revenue minus cost. So then we plug in our two formulas. Profit is the revenue, which was negative q cubed plus 210 q squared, minus, and anytime you subtract cost, what are you going to do? Put parentheses around it. My cost, which is 280 plus 18q. Great. So now we clean that up, put all of our terms in order. Negative q cubed plus 210q squared minus 18q minus 280. There's our profit. And then find the derivative. Because, and I'm going to write it the way they would, MP of Q, marginal profit of Q, is really the derivative of profit. Oh, I've been writing X and it's actually Q. And then that would be negative 3Q squared plus 420Q minus 18. And that's your marginal profit, the derivative of profit. Now to answer this next problem, this is again where I'm talking about being thorough. Being thorough as a mathematician, being thorough as your business manager. It says how many items should be sold to maximize profits. Well, let's find out. Oh, ooh, this is a quadratic. Does anyone else have that same reaction? Like, oh, it's quadratic. What do we have to do? We want to know when this is equal to 0, right? Can we divide by 3? Yes, we can. Oh my gosh, I'm so excited. We can divide by 3. We're going to divide the 3 off. So now we just have q squared minus what? 140q plus 6. Can that be factored? No, certainly not. Nothing multiplies to make 6. That adds to 140. So what do we have to do? the quadratic formula. So it'll be negative b, so negative 140, plus or minus the square root of negative b, I'm sorry, just b squared minus 4 times a times c. By the way, you do have to do the quadratic formula a few times on the test. You don't necessarily have to show a ton of work. You know, if you can do any of these calculations on your calculator, that's okay. But you do want to be very careful. So it's 140 plus or minus the square root of, I normally do this part on my calculator. I'll do the whole b squared minus 4ac all at once on my calculator. I'll do 140 squared minus 24, and that gives me 19,576 all over 2. And then, folks, on my solution guide that I'm posting online, you'll see me draw 2 arrows. Arrows. Yeah, I'm going to give my 2 answers. And I type it, the whole thing into my calculator. I use a parenthesis for the numerator. And I go parenthesis 140 plus root 19576, parenthesis divided by 2. And then that quickly gives me one answer, 96. And then I hit second entry. And it gives me that exact same thing. I just go back and I change the plus to minus. And I get my other answer, which is 0.04. That's very curious. How many different ways can I maximize profit? Apparently 2. But this answer makes sense. If I want to maximize profit, how many units would I sell? 140, if we round to 140. Or how many units? None. This is a pretty funny answer. If you want to maximize profits, either do nothing or sell a whole bunch of things. Well, why are there 2 answers? Is that really a maximum? Is that really telling us a maximum? I wonder what this graph actually looks like. It's negative q cubed plus 210x squared minus 18x minus 280. What? Oh, there it is. Oh boy, this is very big. Oh, there's the graph. So was that a maximum at 0? That's actually a minimum at 0. You see the graph? So one of my maximums, sure enough, was at 139.96. It's right there. You can see it. The other one was down here at, sure enough, 0.0 something. So just because there's 2 answers doesn't mean they're both to maximize profit, right? Because those are just critical numbers. It could be a maximum or a minimum. And in this case, the 0.04 was actually a minimum. That's how you minimize profits. Sell nothing. That's funny. This is funny. How do you minimize profits? Do nothing. That will minimize profits. So the real answer, therefore, was 139.96. So how many items in hundreds need to be sold? 139. Okay. All right. Nicely done, folks. We'll take a quick break. It's 11:08. Let's come back in here at 11:18. Rose, did you get everything from over here? Okay. You what? I can. The real question is, will I? Oh, okay. Where is this? This is athletics. Oh, that's right, Rose. What do you sport again? Softball. Okay.
Yeah. I had to cancel. You need to speak to Lorena or Ty or even Julie. I think Julie wanted to go yesterday. She was gonna call Ty today or to see where they're gonna meet. Okay. I'm just texting him. Oh, okay. Do you know the Samsung? Yeah. I think they said 8 o'clock because we're supposed to be using one of the school. Yeah, but like where 8 o'clock? Yeah, I'm not sure. It was okay. No, my husband did his citizenship and he gets sworn into. And we
Okay, awesome.
we got our appointment on Friday. Remember we met on Thursday? Well, I got the appointment on Friday evening in the mail, so I had to cancel. But that's also right. Yeah, it's right at noon, so I can't do anything in the morning or in the afternoon. Yeah. Go get a jacket real quick. Thank you.
Just out of curiosity,
Yes.
what are those cards for? Like, there are so many card part in there.
Car parts?
Yeah.
Where?
Like part over.
Oh, why are there so many cars?
Yeah.
I don't know.
And those are like without their license plate.
Yeah, no, I mean, those could be the cars,
The workshop works on.
yeah, that they're working on.
The ones in the fence.
Yeah.
So they are going to fix the car or?
Well, theoretically. Yeah.
The hands-on training.
Oh.
Mm-hmm. All right, folks, everybody's back. Let's get started. Go ahead and take out 2.10. 2.10, there's just a couple problems in there that I want to go over. They're interesting application problems. So we're not necessarily learning anything new, but it's a new type of application. The first one is an approximation tool. It's an approximation tool. And so let's go ahead and look at the first problem. We're not going to do number 1, we're going to do number 2. So it says, what? Use a linear approximation, the tangent line, in order to approximate the square root of 327.2. So number 2, we'd like to know what the square root of 327.2 is. Now, on the one hand, you might just say to yourself, well, I don't have to approximate it to find the square root. What can you do? You can just go ahead and square root it. And if you square root it, the actual answer is 18.0886. We call it 18.0887. That's probably more accuracy than we need. So we don't need to approximate this. This is fairly simple. But on the other hand, here's a question. Can you square root in your head? No. And the only way we were able to do that was by actually using a calculator. And so what would be nice is if instead of having this function called a square root, wouldn't it be so much easier if there was just a formula like y equals mx plus b, and instead of plugging in 327.2 into a square root, what if you were able to just plug it in to mx plus b? Wouldn't that be nice? That would be very convenient. Then that is something you can do very easily with scratch paper. You can do it on paper and pencil. You could take 372, multiply it by a number, add a number, and then bam, you would have the square, you'd have an approximation to a square root. So that's the idea, is that sometimes formulas are hard. Like the actual formula could be hard. I realize that a square root is not necessarily hard. But what if the formula that you had for profit, what if the formula for profit was something like negative 1.28 x to the 4th minus, 5 x to the 3rd plus, I don't know, 4.7823 x squared, and then minus 3x plus 1,000. Right? You look at that formula and you say, oh, I don't want to have to plug a number into that formula over and over and over again. Right? Wouldn't it be better if I could just approximate my profit formula by saying, hey, you know what? Approximately, it's just mx plus b. And then you break down that whole formula into just an approximation, which is very simple to calculate. That's our goal. Our goal is, what happens if sometimes you're given a really hard formula, something you can't do in your head, or something you don't want to do over and over, and you're like, listen, I just want an approximation. Okay? That's our goal. So given that that's our goal, let's go ahead and take a look here. They're saying, let the function be the square root of 3x. So everybody, let's draw a nice little graph of that real quick. I'm going to pull up Desmos. We're going to do the square root of 3x. And I'm going to find a window that'll actually let me do that. There we go. So there's our function. And we'd like to approximate that and they're going to ask us to approximate it in a particular neighborhood. But everybody, go ahead and start by drawing your graph. The square root of 3x starts at 0, and it goes up and kind of goes like this. Well, it continues up. There. That's what your square root function actually looks like. And they're asking us, let the function be the square root of 3x. That's the equation we want to approximate. So instead of the square root of 3x, f of x is equal to the square root of 3x, they're saying, boy, I wish I just had a formula, mx plus b, that would approximate that formula. So what formula would be close to that? Well, I'd like you to visualize, just visually, what could that look like? Well, for instance, let me just go back here. It could be, if I were just to do a quick approximation, maybe it would be 1/2 x plus 2. No, maybe 1.5. There, how's that approximation? Is my blue line close to the red line? Well, you might say it's close there. It's only close there. And in fact, what if I zoom in? And if I zoom in one more time, how's my blue line approximation? Pretty good. Pretty good. In that neighborhood, my blue line pretty much gives the same answer as the red line, so long as I stay close to it. And in that regard, it would be way better to have a linear formula instead of the square root. In fact, if I zoom in again, how's my approximation? Incredibly good. So this is why, using calculus, you might want to come up with a formula that's approximately this formula within a certain neighborhood, right? So long as you're only trying to plug in certain values within a certain domain, then you might as well use the approximation formula instead of the real formula because it's so much easier. However, is your approximation formula going to be good for all possible values? No. Because if I tried to use my approximation formula over here, this would have a huge error, wouldn't it? My approximation formula would be very wrong from the actual formula. So what we're trying to do right now is come up with an approximation formula that would work well within a certain range. So go ahead and put a little dot right here. Oh. A little dot right here. Drawing a tangent line. And kind of chunk off from there to there. Right? That's the good region. So, okay, within that region, your approximation graph and the actual graph are pretty close to each other, and you could go ahead and use the approximation graph and save yourself a lot of time and energy of not actually using the real model, but just using the approximate model. Ultimately, we're talking about a time-saving device. We're just talking about a time-saving device. All right, well, we now know what we're trying to do. We want to come up with just a line, y equals mx plus b, that's tangent to that point. And it's going to give us some fairly good approximations for the square root of 3x, provided we stay within a certain window. So how do we do it? We know we want the model, y equals mx plus b. So what do we find first, m or b? M. We're going to always find m first. So what is the slope? Well, the slope is simply the slope at the point that they tell us to find. So what did they tell us to find? They said, let the function that we're trying to approximate be the square root of 3x, the equation of the tangent line at x equals 27. So that's where they want us to find the point of the tangent line is at 27. So what is the slope of the square root of 3x at 27? What would we have to do? The function is the square root of 3x, but we want the slope of that graph at the point 27. So, are you okay, Julie? Okay, so what do we have to do? Since we want the slope, find the derivative. Find the derivative. So first of all, this is actually 3x to the what? To the 1/2. So now let's go ahead and find the slope. So that's 1/2. You bring down the 1/2, you subtract 1, but then it's the chain rule, right? You bring down the 1/2 and subtract 1, but you have to multiply by the derivative of the inside, and the derivative of the inside is just 3. So our derivative is this, and I'm going to clean that up. It's 1/2 times 3 at the end, so that's actually 3/2 times 3x to the negative 1/2. That's our derivative. I can clean that up even more, because what does the negative square root, I'm sorry, what does the negative exponent tell us to do? Put it in the denominator. So I have 3/2. 3 is in the numerator, 2 is in the denominator. What else goes in the denominator? The square root of 3x. So we now have a formula for the derivative. And what do we want to evaluate that derivative at? What point on the graph? 27. So we'll go ahead and find the derivative at 27. So that's 3 over 2 root 3 times 27. And oh boy, this actually comes out pretty clean. That's 3 over 2, the square root of 81. The square root of 81 is actually 9. So this is 3 over 2 times 9, which is 3 over 18, which is actually 1/6. That's a very nice slope. Up 1, right 6, up 1, right 6, up 1, right 6. So we now know that for our approximation formula that we're trying to come up with, it's 1 over 6x plus b. And instead of writing f of x, now let's write y. Why do we want to write y?
So we can plug it in.
Yeah, it's more convenient. We're about to plug in the coordinate, right? We're going to plug in the coordinate for x, y. Well, what is that coordinate? That coordinate has the x value 27. What's the y value? The square root of 3 times 27. That's the actual coordinate there of the original square root graph. So what is 3 times 27 and then square root of? 9. Yeah, it's the square root of 3 times 27, which is the square root of 81, which is 9. So the coordinate right there is 27, 9. That's the coordinate that we're looking at on our square root graph. And so we'll go ahead and plug in those values. 9 equals 1/6 times 27 plus b, and this will help us find our b value. So what is that? 9 equals 27/6 plus b. That's really 9 equals 4.5 plus b. Is that really 4.5? 27/6? 24/6 is 4, and so that's 3. Yeah, that's 4.5. Well, not bad. I'm gonna write 4.5. That's even better. 27/6, if you did it on your calculator, would be 4.5. And therefore, what's b? We're going to subtract 4.5 from both sides. And therefore, b is 4.5. Did I do that right? Is everybody with me? Okay, well, great. We just found our formula. Our original formula, the square root of 3x, can be approximated by a linear model, 1/6x plus 4.5. That's what we just came up with. This is very exciting. Provided you believed me on everything I was saying. That there are certain formulas and certain conditions where the formula is just too hard, and you want to come up with an approximate formula that's easier to calculate, and within a certain window, it gives you results that are pretty close anyway, so who cares? So I'm going to go back to my graph, and let's go ahead and look. Let's see how our graph or our approximation did. It's 1/6 x plus 4.5, and bam! There. The point that we were trying to approximate was 27, and here's 27 right here. Oh, folks, I mean, come on, are you impressed or are you impressed? Look at how closely that blue line hugs the actual red square root graph. Is that not impressive? Is the blue line a good approximation of the red line? Oh, yeah, I mean, you're so excited right now, you're all about to write home about it. Mom, Dad, we did this blue line approximation to this red line today. It was amazing. All right, so what window would we have to be in for that to be in a good approximation? Definitely, that's a good window, right? Anywhere in that window? So anywhere from basically 10 to 45, you could go ahead and just use the blue line approximation instead of the red line because it's pretty close. But if you were to go further to the left than 10 and further to the right than 45, it would be a bad approximation. Like you wouldn't want to come all the way out here. You wouldn't want to keep using your approximation anymore because there's going to be a big difference between your two answers. All right. Well, folks, that's what we just accomplished. We just found an approximation to the square root of 3x in the neighborhood of, go ahead and write that down, in the neighborhood of x equals 27. And folks, what do you think? What should the region that we believe be? Should we only go from, say, 15 to 45? Really, that depends on you, right? It depends on your margin of error. It depends on how much you're willing to be wrong. Maybe you want to zoom in a little bit and say, nah, I like that. The blue and the red line are almost indistinguishable now. I'm only going to use this formula between 20 and 34. But between 20 and 34, my formula is a great approximation. And then you could go overboard, right? Like now, can you even see the difference between the blue and the red line? No, you can't even see the difference now. So you'd say, nope, I'm only going to use this formula between 24 and 31 because it's like spot on. All right, but what did the problem actually want us to do now? Using this, find our approximation for the square root of 327.2. So what's our approximation for 327.2? Well, first of all, we don't just plug in 327.2 into this model. Remember, we're modeling the square root of 3x. So if we want to find the square root of 327.2, we have to rewrite it as 3 times something, because that's the x value. So 327.2 is really 3 times what? How would you find that? How would you find it? Yeah, just divide 327.2 divided by 3. So we're really saying 109.06. 66666. So that's the actual x value that we then plug into our approximation model. So let's see what happens. If I plug in, we know that the answer is supposed to be what? 18.09. That's what the answer should be. But what does 1/6 of 109.066 plus 4.5 give us? It gives us that divided by 6, 4.5. It gives us 22.67. Is that a good approximation? Nate?
I'm confused. Do we have to do all of that, or
Did we have to do all that? Yeah.
to find the answer? Because aren't we just dividing
Yeah,
all of it?
to find the approximation for 327.2. To find the approximation, they want us to use our model.
So what's the answer for the approximation?
Our approximation is 22.67. Our approximation using our linear model is 22.67, which wasn't very good, was it? No, not very good at all.
What were we comparing to?
What are we comparing it to?
Yeah, like what were we?
The actual square root is 18.
Oh.
Yeah. Now I can show this to you on the graph. We were trying to square root. Oops. We were trying to square root. This is the square root of 3x. Yeah. And we're looking at our x value of 109. So look at the graph at 109. See, 109 fell way outside of our boundary, didn't it? See, like there's 109 on the graph. How far apart is the approximation and the true graph? Pretty far apart. And besides, didn't we say earlier that we really only wanted to use our approximation if we were within the neighborhood of x is between, say, 20 and 40? So we were trying to approximate an x value that was way outside of that window, so of course our approximation was not very good. But let's say that we wanted to square root something that was within our window, like from 20 to 40. Why don't we try an x value of, say, 40? What if we were actually approximating an x value of 40? So that means, I'm all out of space here. If I wanted to square root 3 times 40, that's actually the square root of 120, which is, 10.95. Or I could do 1/6 of 40 plus 4.5, and that would equal 11.16. Now how is that approximation? That approximation wasn't bad at all. And all things considered, someone might very well want to use this instead of this as a model. Okay. What questions would you like to ask about that?
Oh.
It just seemed kind of long. Yeah.
Yeah, and especially because of the fact that because we're doing 3x, that you have to divide off the 3 to see what number you're actually looking at, and then plug that number into the 1/6. I totally get that, and I see that. Okay, well, I tell you what. Let's just let that sink in for a second, and let's go look at the second application, and then we can always come back and revisit that.
So which one would we put down, like if we had this on the test, would we put down the answers 22.6 repeating?
Yeah. Yeah, that's our approximation to the square root of 327.2. We can come back to that. Okay, turn the page, and we're going to look at number 3. To do number 3, we're going to take some notes, and we're going to put our notes right there on number 3. Oh, good, and I put that right there for you, that photocopy of all that information. Okay, good. First thing I'd like you folks to do is right below your photocopy where it has the little box, we're going to make a number line because I want to teach you or show you what elasticity means. Maybe you already know because you already read your textbook in section 2.10, so you're already familiar with this, but let's go ahead and look at it together. Make a number line. We're going to call it our elasticity number line. Elasticity. And what it says here is we're looking at something called the elasticity of demand. That is demand elastic? What that means is if I raise the price, are my customers going to come with me and I'm going to increase my revenue? Or if I raise the price, are my customers going to abandon me and I'm going to lose all my sales? Because they're like, whatever, forget this. You raised your price. I'm not going to buy your stupid product. So that's what we're trying to determine is the elasticity of demand, which is the elasticity of our customer. How stretchy are they? If I raise my price, can I make more money off of them? Those suckers? Or if I raise my price, are they smarter than me and they're not going to buy my product? So is that fair? That's what we're talking about, the elasticity of our customers. How much can I essentially pull their money away from them? So that's elasticity. So given a demand function that gives the number of products in terms of P. So remember from earlier, the demand function is P in terms of Q. That is the price that you should charge in terms of the quantity that you are going to sell. They're actually suggesting that we flip-flop that. They want a demand function that gives Q in terms of P. So what we're actually going to do is how many products should you sell in terms of the price that you're charging. So they're asking us to flip-flop what we used to do. Instead of the price, the demand function equaling the price, now our demand function is going to equal the number of products. Elasticity is defined as this. This looks pretty funky, but everyone write that down now, right below the word elasticity. E equals the absolute value of price divided by quantity times the derivative of our demand function. That's elasticity. That is a funky equation. You take your price divided by the quantity of how many you're going to sell, and then you multiply it by the derivative of this demand formula that they're going to give you. They're going to give you the demand formula. So what is this value going to equal? It's going to equal some number that's either going to be equal to 1, or it's going to be less than 1, or it's going to be greater than 1. That's what your elasticity formula is going to spit out. Well, I mean, I guess that's obvious. Any formula is going to spit out a number, and it could either be 1, or it could be less than 1, or it could be greater than 1. But this is the range that we're looking at. So it's either going to be some small decimal, it's going to be equal to 1, or it's going to be some big number. Well, if E is less than 1, so this is why I have a number line here. Theoretically, this is 0, and we're going up to 1, and then we're going past 1 to infinity. Okay, so there's our number line. We're really just focused between 0 and 1, and then beyond 1. If E is less than 1, we say the demand is inelastic. Inelastic. Demand is inelastic. And what that means is that raising prices will increase revenue. So you want to put that. Raising prices raises revenue. Is that a good thing or a bad thing? That's excellent, right? This is awesome. I can raise my prices and all my customers are still going to buy my products and I'm making more money. This is awesome. Inelastic is a very, very good thing. I put a smiley face. I love when my customers are inelastic because I can just raise my prices and make more money. I don't have to do anything to my profit at all. I mean, I don't have to do anything to my product at all. I don't have to make it better. I don't have to make more bells and whistles. I don't have to advertise more. I don't have to do anything. All I have to do is raise my price. That's a good day. Okay, so then if E is greater than 1, we say that demand is elastic. What's that, Nick?
I'm saying like Apple.
Oh yeah, Apple. Exactly. Apple can do whatever it wants. The American people are definitely inelastic when it comes to Apple products. I have an Apple. Okay, so if elastic, raising prices decreases revenue. Raising prices decreases revenue. What does that mean? You just raise the price on all of your customers, and what did they do? They're like, whatever, man. I'm not going to buy your stupid product anymore. And I'm going to put a frowny face there, because that's bad for you. You were like trying to pull a fast one on your customers, like, I'll just raise the price, maybe no one will notice. Oh no, they noticed, and they abandoned you. They're not buying your stupid product anymore. Now, if E is actually equal to 1, we call it unitary. Unitary. Which means, well, raising your price won't raise the revenue and it won't decrease the revenue, so you might as well not raise the price because it's not doing anything for you. All right. Well, that's the main idea. That's the main idea. This is going to help you make a business decision. You know, you're sitting there wondering, should I raise my price? Should I not raise my price? And so you calculate the elasticity of your product. And then that is going to tell you if you should raise your price or not. Definitely over here, you should raise your price. Over here, don't raise your price. Okay, well, let's try it, folks. Let's try it with our first problem. You now see it. Is it right down below? Is it the square root of? Yeah. So here's our first problem. We're going to look at the demand function, d of p, is equal to the square root of 325 minus 2p. I just want you to notice that this demand function truly is flipped now. What does p represent? The price. So in other words, p is the price, and so what does this whole thing equal? Number of units or quantity, right? That's the inverse of what we used earlier as our demand function. All right, well, that's it. That's the formula, and they're saying find the elasticity of demand if you charge $6. This is really cool because we're saying, okay, what if I charge $6? Should I charge more or less? Like 6 is just my starting point. I want to charge $6, but could I charge more than that, or should I stop at 6? So let's go ahead and calculate it. We have our E formula, and elasticity is the absolute value. Well, P is our variable, so it's just P. Let's definitely finish this one, if not one more. All right, so P over Q, well, that's actually what the D of P stands for, folks. D of P is Q. That's the formula for Q. That's the formula for the number of units. So we're going to put our formula down there, 325 minus 2P. You might want to make a note that D of P is actually Q in this formula. In fact, you could even change the formula if you wanted to and say that the formula is P over D of P times actually D prime. That might be a way more helpful way to think of this formula. I don't know why they didn't just give it to us like this, but that's actually what we're about to do. Okay, so we put P over D of P, and then we multiply by the derivative. Well, we now have to go ahead and calculate the derivative of this. That's really what? 325 minus 2P to the 1/2. So we need to take the derivative of that. The derivative would be 1/2 times 325 minus 2P to the negative 1/2 times negative 2. because the derivative of the inside function, we're doing the chain rule, the derivative of the inside is -2. Okay, so what is our derivative then? It's -2 times 1/2, that's -1. And this -1/2 means the rest of it goes in the denominator, the square root of 325 minus 2p. So that was our derivative. And so now let's go back and finish calculating elasticity. Sorry, that was a little, we started off doing elasticity and they're like, oh wait, we need the derivative. So we did the derivative, but now let's come back and finish calculating elasticity. Elasticity now, I multiply by the derivative, which is -1 over the square root of 325 minus 2p. Okay, this is our elasticity formula. Does that clean up pretty nicely? What do you think? What's the numerator? -p. And what's the denominator? We're multiplying a root times a root. Yeah, the root cancels out. This is really root 325 minus 2p squared. So the square root cancels out, and it's just 325 minus 2p. Well, that is our formula for elasticity. And what did they want? They wanted to evaluate elasticity at what number?
6.
At 6. So we go ahead and we just plug in 6. So that's -6 over 325 minus 2 times 6 is 12, which is -6 over 313. And the absolute value of a negative number is positive, and 6 over 313 is clearly a very, very small fraction, meaning a very small decimal. So what does that tell us about the elasticity of our customer? Yeah, the E value turned out to be very small. It was quite less than 1, and therefore we can raise prices, and that will raise our revenue.
Where did the -6 come from? Oh, never mind. Let me answer that question.
Okay, good. Okay, I hope everybody liked that application problem better than the square root one. Did you like that application better than the square root one? It was at least a little more straightforward anyway. Shoot, I would really like to do one more of those with you, but it's 11:48. I realize that class ends at 11:50, but I'd like to do one more of them. So I think what I'll do is I'm going to go ahead and do one more of them. And you can all make your own personal choice as to whether or not to stay. It will only take a maximum of 3 minutes. We don't have to explain any of this. We just have to do the problem. So let's just do one more. And I'm telling you that we can use this formula. Even though the book gives us this formula, this is obviously what we're actually doing. So I'm going to erase that. Erase all that. We're going to do one more.
So if it's inelastic, you can raise the prices.
If what?
If it's inelastic, you can raise the prices.
Yeah, exactly. If it's inelastic, you should raise it. Oh, yeah. At this price, we know it's inelastic, and based on that to increase revenue, we should raise the prices. Okay, here's one more. We know now what to do. We're just using this formula, and they're saying that D of P, oh, this one's so fast. We might even finish on time, is 200 minus 4P squared. And they'd like us to find elasticity when the price is 7. So what should we automatically do? Find the derivative, because we know we're going to need the derivative formula. So the derivative is -8p. And now we can go ahead and find our elasticity formula. It is P over our formula for demand, P over 200 minus 4P squared, times the derivative of demand. You notice how I put that -8p in the numerator. I put it over 1 to remind myself it's in the numerator. It's going to get multiplied by that other p. And so my elasticity formula is -8p squared over 200 minus 4p squared. All right. And so we're going to plug in what? 7. Yeah, we're wondering what's the elasticity at 7. So -8 times 7 squared is -392. And then 200 minus 4 times 7 squared is 4. Ooh. And -392 divided by 4 is negative 98, and the absolute value of a negative number is positive 98. That elasticity was a very large number, and therefore it's elastic, and we should definitely not raise the price any further. In fact, if it were you, and you have such a large elasticity value, what would you probably do with your price? Lower it. You should probably lower it. How far would you lower it? Until your elasticity is 1. So in fact, elasticity of 1 is really your goal, isn't it? You've raised your prices as much as you possibly can without losing revenue. Okay, thanks, folks. See you, Nate. Nate, thanks for your questions today. Oh, nobody has left yet. Good. David, here's your papers. Thomas, here's your papers. Okay, folks, I will post a Canvas announcement today. It will have the solution guide to the whole practice test. And then when you come in on Tuesday, again, you guys get to work with each other and with Douglas to review any questions you have.